Imagine performing an autopsy on a solar system that died billions of years ago. Imagine sifting through the wreckage of a cosmic collision to figure out, element by element, what an alien planet was made of. This isn't science fiction. This is a real field of astronomy called stellar forensics, and it's one of the most exciting frontiers in our quest to understand the universe. Today, we're diving into the science of reading the last breath of dead stars to unravel the violent deaths of planets and stars alike. Welcome to G Fun Facts Online. In the vastness of space, the universe is filled with stellar corpses. For stars like our own Sun, the end of the line is an object called a white dwarf. Over 97% of all stars in our galaxy will end their lives this way. So, what is a white dwarf? After a star burns through its hydrogen fuel for billions of years, its core collapses, heats up, and it swells into a red giant. This phase is destructive for any nearby planets. In about 5 billion years, our Sun will do this, swallowing Mercury, Venus, and possibly even Earth. Eventually, the star runs out of fuel entirely. It sheds its outer layers in a beautiful display called a planetary nebula, leaving behind its hot, dense core. That core is the newborn white dwarf. Now, this isn't just a burnt-out rock. A white dwarf is an object of extremes. It packs the entire mass of our Sun into a sphere roughly the size of the Earth. The density is staggering. A single teaspoon of white dwarf material would weigh as much as a school bus. This density comes from a state of matter governed by quantum mechanics called electron degeneracy pressure, which halts the star's collapse. The immense gravity of a white dwarf has another crucial effect. It sorts everything by weight. Heavy elements like iron or silicon sink rapidly towards the core, while the lightest elements, hydrogen and helium, float to the top. This creates an incredibly pure, thin atmosphere, sometimes just a few dozen meters thick. This pristine layered atmosphere is the key. It's a perfectly clean slate. Any element heavier than hydrogen or helium found there is a foreign contaminant. It's a clue. It's the evidence of a crime. We are looking at a cosmic crime scene. So, what kind of cosmic crimes are we talking about? For a huge number of white dwarfs, somewhere between 25 and 50%, their quiet retirement is violently interrupted. Their atmospheres are polluted with the remains of objects they have recently devoured. The most common scenario involves the wreckage of the star's own planetary system. When the star became a white dwarf, it lost a lot of mass. This can throw the orbits of surviving planets, asteroids, and comets into chaos. Gravitational nudges from larger planets can send smaller bodies, like asteroids, on a collision course with the white dwarf. If an asteroid gets too close, it crosses a point called the Roche limit. Here, the white dwarf's tidal forces are stronger than the asteroid's own gravity. The asteroid is torn apart, shredded into a stream of dust and gas. This material doesn't fall straight in. Instead, it forms a swirling disk of debris around the white dwarf, like a miniature version of Saturn's rings. Over time, this disk material spirals inward and rains down onto the star, polluting its once pure atmosphere. Because the white dwarf's gravity is so strong, these heavy elements should sink out of sight in a very short time, astronomically speaking, from days to a few million years. So if we see them, it means the star is actively feeding. We are witnessing the digestion of a planetary system in real time. This gives us an incredible opportunity. We can't drill into the core of planets in our own solar system, let alone exoplanets. But here, we get to analyze the bulk composition of a completely vaporized alien asteroid, piece by piece. We're doing geology on worlds hundreds of light years away, a field we now call exogeology. But it's not just planets and asteroids that collide. A huge fraction of stars are born in pairs, and so we often find two white dwarfs orbiting each other. As they dance, they radiate gravitational waves. just as Einstein predicted. This causes them to lose energy and spiral closer and closer together until they violently merge. The outcome of this double degenerate merger depends on their mass. If the combined mass is large but not too large, the smaller white dwarf gets torn apart and absorbed by the larger one. This creates a single ultramassive white dwarf that's rapidly spinning and highly magnetic. The forensic clue here is subtle but brilliant. The merger is so violent it can burn off most of the normal hydrogen and helium outer layers, leaving an incredibly thin atmosphere. This allows elements from the star's carbon-oxygen core to be dredged up to the surface. Finding carbon in the atmosphere of a massive white dwarf is a smoking gun for a stellar merger. However, if the combined mass of the two merging white dwarfs crosses a critical threshold, about 1.44 times the mass of our Sun, something far more spectacular happens. This is the Chandrasekhar limit. At this mass, electron degeneracy pressure fails, the core collapses, temperatures skyrocket, and runaway carbon fusion begins. The entire star detonates in a cataclysmic explosion known as a Type Ia supernova. These explosions are so consistently bright that astronomers use them as standard candles to measure the expansion of the universe. So these stellar autopsies not only tell us about dead planets, but also help us understand the cosmic explosions that map out the cosmos. So how do we actually read these clues from so far away? The primary tool in the stellar forensic kit is spectroscopy. We take the light from a white dwarf and pass it through a prism-like instrument, splitting it into its full rainbow of colors. Atoms in the star's atmosphere absorb light at very specific wavelengths, creating a unique barcode of dark lines in the spectrum. Every element, from calcium to iron to silicon, has its own unique spectral fingerprint. By analyzing this barcode, we can identify exactly what's polluting the star's atmosphere and in what quantity. We need different tools to see the full picture. Ground-based telescopes using visible light are great for finding common elements like calcium. But for key elements like carbon and silicon, we need to look in ultraviolet light, which is blocked by Earth's atmosphere. This is where space telescopes like the Hubble Space Telescope are essential. And for studying the dusty debris disks themselves, we turn to infrared light. The dust is warmed by the white dwarf and glows in the infrared. The James Webb Space Telescope, with its incredible infrared sensitivity, is revolutionizing this field, allowing us to identify specific minerals in the dust, like the silicates that make up rocks on Earth. Let's look at a few case files from this cosmic morgue. One of the first and most important cases was a white dwarf called G2938. In the 1980s, astronomers detected an excess of infrared light coming from it. This was the signature of a warm, dusty disk of material, likely the pulverized remains of an asteroid. Its atmosphere was also polluted with heavy elements. G2938 was the object that first firmly linked atmospheric pollution to a surrounding debris disk, becoming the prototype that proved this entire method works. Then, in 2015, came one of the most spectacular discoveries, a white dwarf named WD 1145 plus 017. Using data from the Kepler mission, astronomers saw something incredible. The star's light was dimming periodically, not in the neat, predictable way a planet would, but in deep, irregular, and rapidly changing dips. These transits were caused by large clouds of dust and debris from a disintegrating asteroid orbiting the star every 4.5 hours. An orbital period that's short means the object is deep within the star's gravitational grip, actively being ripped to shreds. We are literally watching a world get torn apart in real time. It's the Rosetta Stone that connects our theories of planetary destruction directly to observation. Another fascinating case is a white dwarf merger remnant, WDO 525 plus 526. In visible light, it just looked like a normal, very massive white dwarf, But when Hubble looked at it in ultraviolet light, it found the faint but unmistakable signature of carbon. A normal white dwarf should have carbon on its surface. It should be buried deep in the core. This discovery, combined with its unusually high mass, was the smoking gun. This star wasn't born, it was made, forged in the collision of two smaller white dwarfs billions of years ago. These discoveries are more than just cosmic curiosities. They have profound implications. By analyzing the elements in polluted atmospheres, we are doing exogeology. We've found the remains of rocky bodies similar to those in our solar system, rich in oxygen, magnesium, and iron. Many of these appear to be fragments of larger bodies that were differentiated, meaning they were big enough to have melted and formed a metallic core and a rocky mantle, just like Earth. This tells us that the processes that built our planet are not unique. They happen elsewhere. The fact that up to half of all white dwarfs show this kind of pollution tells us something fundamental about the galaxy. It means that the formation of rocky worlds and the larger planetary systems needed to deliver them as debris must be incredibly common. Finally, studying these dead solar systems gives us a chilling preview of our own future. In about 5 billion years, our Sun will become a white dwarf. The outer planets will survive in wider orbits. The asteroid belt will still be there. Over billions more years, gravitational nudges from Jupiter will likely send some of those asteroids careening into the dead Sun. An alien astronomer, 6 billion years from now, could point their telescope at our solar system and see a polluted white dwarf. By analyzing the light from our dead Sun, they could read the chemical signature of our asteroid belt, the final ghostly echo of the building blocks that formed Earth. In the end, white dwarfs aren't just dying embers. They are cosmic storytellers, active crime scenes that hold the chemical ghosts of destroyed worlds. And by learning to read their stories, we are piecing together the history of the cosmos, one dead solar system at a time.